Hi everyone. I'm making a video on a data science challenge. It's called BraTS Challenge, and basically, University of Pennsylvania has been doing this challenge for about 10 years with other institutions where they take MRI data of tumor brain scans to do essentially a public data set release for data scientists or computer scientists, where essentially they will develop deep learning frameworks to take on that challenge. Oh God, so unnatural doing a video. Anyways, yeah, I want you guys to join me on this journey. I'm going to be joined by my two teammates, Nathan and Rishak, and we're going to try our best to take this on. We do have a group name. Essentially, we're teammates from Open Vessel, which is kind of like our startup open source community for doing data science projects, software development around medicine. We're going to do today, though, this week, because the challenge has started on the 7th. I'll be recording kind of our whole experience and what we'll be actively doing. I'll say this first. We're all grads, or I should say undergrads. So, like, I've graduated, but the rest of my team are undergrads. So we kind of met at Penn State, and now we work closely together on Open Vessels. So yeah, this is taking on the BraTS challenge. Challenge breakdown. I recently got the email, and here is the tumor subregion segmentation, where basically they want us to read in images and then do pixel segmentation on top of those images to help classify the tumor. So, when you kind of like look at the tumor image, you're going to take a group of pixels and get them labeled so a deep learning model can classify them in the second task. And they want that according to a promoter or methylation status. I haven't read in this yet. We need to explore these definitions more and what their technical meaning is. But I'm going to show you an example of classification for a different form of radiogenomics. But here, basically, from my experience, I was educated in biotechnology, where essentially methylation is just the addition of a methyl group on maybe a molecule or biomolecule. Where if I'm guessing this promoter is kind of like a contrast agent, maybe, but I could be wrong. Anyways, this is our to-do list for today. We're going to make some pre-processing code with the test data, because that's a really important step where we need to read in all the data, get it prepped for the deep learning model, if that's going to be in numpy arrays or data frames or PNGs, depending on what other groups are really doing. We can do some research on that. We're going to prep the GitHub repo, and then we have a typo, Docker setup. So a really important thing about this challenge is that they expect all of your work to be submitted into a Docker container with very specific inputs and outputs. So that kind of adds on to the work for what we might have to do, but it's really no big deal. We can get that done, and hopefully I'll get that done today. So we're going to meet the team after work. A lot of my guys were all part-time because we're college students and we have to pay loans or bills, including myself. We're going to have to do this after work. So yeah, that's going to be what we're going to do today, and we're going to fill out each of these sections. So that's it. Hey guys, what's up? So I've sped up the footage. So I'm making the GitHub here, the repo. Not very creative with names. I was kind of not feeling very good when I was recording that day. So um, yeah, I'm basically going through the competition information, collecting research papers. Essentially, what I do is that I want to get a good idea of what researchers have done already, and probably what the best methods are and what their current state of development is. So the footage is glitching out here, unfortunately. But I'll open up a few Google Docs for my teammates, make some notes, do some reading, make a works cited, because over time, when you like wake up every day and try to read a research paper, you'll kind of forget, where you read a specific piece of information. And you should cite everything you learn, or everything that should be part of the project. A lot of the times, it's taking different pieces of information and pulling them together for a solution, maybe, or you learn something, or it kind of fits into the greater story. Here I'm developing the PowerPoint to explain the context to the rest of my team and what that potential might hold out to. I went off to go get coffee because we had to sit there and wait for a download to happen. So probably cut some of this out a little bit. So I found a data set, I think, from 2020, and there's just unzipping it. Now I'm watching some video on some of these low-grade tumors and what they kind of look like and what their definition is, because I have no idea what I should be looking for. And hopefully we can email a radiologist or some researchers more information about this and see if they'll talk to us. I found this video interesting. It was just, he has like a boot camp, how to read CT scans, and manipulating the contrast to see different windows of the brain or bone. You can actually miss a lot in a CT scan, it seems, if you don't go through very what he calls a methodical top-down step, where he starts from the top of the brain to the bottom, and then he explains the different regions, like these cisterns and these like midbrain, cerebellum. I'm blanking there. And how they all kind of relate, like what is normal and what's abnormal. Really, a lot of the time, the brain, when you like get a concussion, will move blood around, and your brain is like adjusting to that pressure and volume. And he kind of hits on a very important note, I think, about this data in general, is that like when you get an injury, your brain is like compensating for the injury by moving some of its volume to the injury. So like like half of your brain will shrink to compensate blood on the other side, or what they call CSV, or fluid. I'm getting a Steam message. It's my friend John in a minute. Okay. So there's some pre-processing tools I found. There's called the BraTS toolkit. Essentially, what's going on is that they made a Docker application that deploys previous models from 2020 that you can use through a Docker container. Unfortunately, I don't have a GPU to use some of these models, so I only can use models that allow CPUs, and I'm excited to see what they can do. I've emailed the guy on GitHub, and basically I'm trying to get a bigger picture of what's going on, collect and investigate as much software as possible and make it into a list, and day by day get through the reading material, because there's a lot of research papers you have to sit through to make the project really work out. And then finding code is another thing. I think I would prefer to write it from scratch, but I shouldn't reinvent the wheel, essentially. So yeah, I like to make some templates for my team and myself, introduction methods and things like that. Here's our joke. This is the BraTS data set. It's BraTS, like sausages, German. Yeah. So collecting more papers, looking at what past consensus has done. 3D UNet is really popular as a solution, and essentially we can see that there's pipelines on GitHub that were developed back in 2020. Those are things you might want to try to run or email the developers on those projects. There's a guy, I think he's in Denver, or I forget. His name is Ellis. He develops like a 3D UNet that does segmentation of these types of tumors. It's a really cool project, and they have a Slack, and you can email them and things like that. So hopefully we'll get a chance to do that. Yeah, so when I download the data, it's stored in something called hierarchical data format, or like HDF5. Essentially, it's a more compounded data. And I thought this wasn't really correct. It was a little confusing. So I need to unpack that data with some code possibly, or go find the correct data set. So here I slowed the footage down, but basically in the links in the YouTube, you can download the data from these links I found. Basically, they have the data, I think, on like an AWS container out there, or like S3, whatever it is. And you can download the zip files of the 2020 set. And then you can start developing a deep learning model to achieve some segmentation, do some testing and development, try to learn these techniques that researchers are currently doing. Some projects are open sourced, others not so much, but they are described in the paper. But we want to get a good sense of what techniques they're developing. And I think it comes down to workflow development every time, and how one function is affecting the next, and things like that. Yeah, right there. I'm highlighting the link and going to it. I found it in the README. So they sent you a README file, and then you go to the URL, and they let you download the data. It was really, yeah, it took me a while to find it, and applying for the data, and it was really convoluted. It's not like you downloaded PNG from Google Drive. It was like just so many steps and so many windows that, like, I think a lot of developers I think would give up by this time and just realize, like, oh, okay, I can't find this data. And since they've been doing this for 10 years, there's lots of different data sets, and there's even torrents out there of this brain data. But I'm really excited to play with it. Putting the links in the PowerPoint and in the YouTube video. And they're downloaded, but we want to really get cracking and get them open or processing into a model and see what might happen, or what the best approach might be. So there's a lot of setup work, I would say. There's a lot of preliminary, like, okay, we need to see what's going on, what the best method is, things like that. You can see it's really stressing me out, probably. So that's what they look like. They this list of folders, and each folder contains a zip file. So that means I have to for loop through all these folders, open all these zip files up, and then move them into Python objects, or however they're going to get consumed. Been looking at something called TF records, where it's like TensorFlow has its own like binary format. We can convert into that, but we still need to find out. Currently, when I'm editing this, I still have to spend time to learn what everyone else is doing, and seeing if it's like worth it, or like, okay, is this agreed upon as like the consensus of like, okay, we want to convert to this format no matter what. And that's the thing, is a lot of the data is in DICOM, and then it goes to PNGs or Nifty, and it's there's a concern that you'll lose data by converting from DICOM to PNG. But PNG images are so much easier to process compared to like the amount of data in DICOM. So you can't like get a definitive answer, but you gotta keep going and I think for next week we're going to write TensorFlow code. We're going to try out a model called Deep Labs that I'm really excited about, because it would auto generate and label pixels, try and make an attempt to identify, or we could customize the data set a little bit more. Yeah, so right now I'm just coding and testing things out. Um, Basically, off to my left, I'm using Stack Overflow like every other developer. And what I'm doing is that I'm trying to for loop through the folder, read in all the string paths, and just automate the process of pre-processing the data. Surprisingly, if you convert data and you move it to like a binary conversion, um, you have like a threshold cutoff point. It's kind of hard to describe what I'm talking about. It's better with images, but basically, if I convert a slice from a CT scan, we can do something called binarization, where we're converting pixels to black and white pixels. And when you convert the data in pre-processing, that can happen, or you're affecting like the HU value. So that's really the biggest concern in my mind, and like how are people HU clipping the data. And then there's MRI data in this data set, so that has to be kind of accounted for. I know there are CT images currently in it. I'm pretty sure, could be wrong, but yeah, I think we're coming to the end here soon, where basically just um, all right. So is it recording? Yep. All right. So we're going to take on the BraTS challenge. And what this is actually a multimodal brain tumor segmentation data set. And it's been around for 10 years. So I think they started in 2011 or 12, and UPenn runs it. And basically, there's some restrictions, like you can't really add more data to the data set, or you can only publish the results that your model is generating until the competition is over. That's about it. All right. BraTS. Okay, why are we doing this? Again, great learning experience. There's $60,000 in prize pool money, but there's only 3 winners for first, second, third place. And we don't have a GPU still. The 380s and 370s are going for $1,000 now, so it'd be really nice if we have this money. And then this is the team we're going to do it with. We're going to do this with Nathan and Rishak. Until I hear from Alex, I've been messaging him, but no response. And other people on the team. This will be the team. All right, so this is the challenge. Basically, you have task 1, where you're doing tumor subregion segmentation, and task 2, where you're doing classifications of those tumors. So they're actually 2 separate jobs. You don't need to do both. You're allowed to just do one to win, the competition, which kind of doesn't make a whole lot of sense, from what I can tell. Or you can just do task 2 at kaggle.com. But task 1 is on a separate platform called Synapse. Oops. All right. So did I go too far? Okay. So I want to talk about classification, what that is. So you know what LRAS classification is? When we look at observation on a tumor, they measure the diameter or circumference, and that can help them determine what grade of that observation is on the liver. So they call it LR4 or LR5 as malignant. So you know about that already. So collecting data, you can download data at this Kaggle link. It's 7 gigabytes apparently, but you have to unpackage things. It's put into a special data format called HF5 or HFD5. or you can go to these links directly and it will automatically download the data in a zip file. All right, so I made a to-do list today. I downloaded the data from 2020 to get ahead because you cannot download the data that was released this year yet, because you have to request for that data. So you have to fill out a Google form and then they'll send the data to you. So to kind of like just get ahead on the process and write some pre-processing code, I downloaded the data from 2020. I prepped the GitHub repo and there's Docker set up. And then my plan was to meet you guys after work. So this is their timeline. The competition just started on July 7th, and they'll release the training data and ground truth. And it will go through August, and everything kind of comes out near the end of the year. Okay, so like I said, downloaded the data. I'm waiting. It's kind of inaccessible right now. There's old data sets and torrents out there if we really want to play with that, but I just don't think it might be worth the time. I did not get the data set description done. All right, so this GitHub repo is up right now for you to download. Did my phone go off? Okay. And here's some pseudocode for pre-processing. So this is what the file system looks like. You have Excel files that contain information like whether or not that patient survived and like where that methylated mapping is, things like that. And then they're in zip files, and essentially each zip file is a Nifty file, so everything is just in a Nifty file. So for the pseudocode, we'll just for loop through all the files, skip over the CSV files. I wrote this code already. And while in the file, we will list all the paths to each one and output the name of the path and then pre-process it. So yeah, that's it there. There's some more things we need to figure out. I found a pre-processing toolkit called a BraTS toolkit, where it will output Nifty files, PNGs, registration, other things. They also have segmentation included, but there's some issues with that I found. So you might just want to homebrew segmentation, which I'll get into that later. This is how their toolkit works. They take in the raw DICOM or Nifty file, and then it's co-registered. So there's different types of imaging called T1, T1C, and T2 that relate to the same image, or FLAIR relates to T1. So that's what co-registration means. And then, they have to pass this through CPU or GPU to do the brain extraction or defacing, where essentially you're making a mask of the brain, where you would apply the mask on top of the brain and then segment out the region of interest, because you only want to look inside the brain. That's a pretty common concept, so it's nothing crazy. So this competition actually requires a Docker container, which there's actually this massive 6 steps to make your container. It requires specific inputs and outputs to specific folders. And then you have an entry point for your script, where it's like you run this script specifically. And then you have to submit the Docker to their Docker repository afterwards. So to like really officially submit to the competition, we need to follow these steps. So I've gone ahead and do that. I'll show you a little bit later. So potential toolkits and software, deep learning frameworks. I've actually looked into this like last year, but I didn't join the competition because the competition was already over by the time I knew about it. There's assemblers, where it's like a bunch of models that work together and kind of like vote which is the best result. Then there's 3D-UNet for PyTorch and TensorFlow. And then there's a pipeline attempt from 2020, which is pretty good. And then the original UNet. UNet has won for the last 3 years in this competition. It's very popular, and it's very familiar because of like how it just deals with the unique data and how all the cells and labels are clumped up so close together. So there it is working. Then there's another model I want to try called Deep Lab. I don't know if that's specifically from Google, but it's been around for a while, and they do generalized segmentation. There's me, and then the segmentation labels it generated. So this is from their demo, and it labels whether or not there's a person or vegetation, things like that. So I'm trying to get that to run today. I have some errors I have to work through, but kind of tired today, so I couldn't break through. So I tried passing like a lung scan through just to see what would happen, and it didn't work too well. It partially labeled it as a person, so um, obviously the Deep Labs model. I've read into it. It's like a dilated convolutional neural network. What that means is that like when when the padding is passed through the neural network, it's like dilated, so it's skipping some pixels a little bit more. And basically, yeah, what was I gonna say? Yeah, Deep Lab 2 is made for like people and vegetation and like live video stream of like you know photos of like cities, buildings, trees, and people. It's not made for like medical imaging. But the unique thing about Deep Labs 2 is you can make a custom data set and then like start using Deep Labs from there on your custom data set and see what you kind of get. So I think this is a pretty useful tool that we could try. And then this is the toolkit I mentioned earlier. There's like a workflow that we kind of flew over. There's segmentation. It can do follow. Uh, there's a form of fusion where it like puts together all those different image types. Yeah, I didn't get a chance to go through it. Some general definitions. So there's different types of tumors. There's enhancing tumor where it's contrast around the tumor, and then core tumor, and then whole tumor. So what they want you to segment in the challenge in task one is essentially segment the core of the tumor or the area, the parts around the tumor, like there's dead tissue, and this is what they're kind of talking about. So like we stop for a minute, this light blue part is the core of the tumor, and necrosis can be inside, or your enhanced could possibly like be like on the outside here. So like they want all of that, if that makes a sense. They wanted segmented subregions. Then there's this description behind the subregion segmentation, which is kind of confusing, and we kind of need to talk about and figure out and what they're getting at here. But I think the image gives the best idea of what they really want. And then assessment. So when your model trains or runs, there's two methods of assessment they have. Essentially, we need to find that Python code and assess the model, obviously on our own time some way, or like find the code that they're using to assess models, or just wait for them to assess our model, things like that. But they're using dice score similarity and Hansdorff distance, so we'll have to find code for that. Excited, more videos to watch, and this was bugs I had with Docker. Okay, so that was it. So that's, oh, I should actually show you. Uh, no, why? No, I have it on OBS. Yeah, 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 yeah. Because my plan is actually to document our journey on this challenge and see how that goes. Because I think that would be really cool to do, and like, you know, I don't know. I think it's a good idea. There's something we could do with that there maybe, and see, if we fail, we fail. All right. So I made the GitHub repo. Just ignore the name. I couldn't come up with the name, so I just did a random generator. It's called Saint Bernard. It's on OpenVessel, and you can download it. What's not in there is the Deep Lab stuff, which is using something called a Cocoa API, which is it's basically an API that calls image data from a database out there of like millions of images of trees and parks and things like that. Deep Lab is just a collection of different models, And then models is just more models from, it's like for loop code for like Orbit. And then what we worked on today that was really important is the Docker file. So you should be able to run this Docker file on your MacBook and get all the packages that we have installed. And this is how they want the Docker file to run, specifically like having these parts in here and all of your required software installed and it being Ubuntu by default. So like when we experiment with like Deep Lab 2 or 3D UNet, we need to keep in mind the installation requirements and put them into the Docker file before submission. And that's about it. And this Docker file should make things easier because I don't have to like pip install 500 times on other computers. We can just download the Docker file on our Ubuntu network. Like our other, like I have a Ubuntu computer in the basement and one next to me and another one in the basement. So like we could just use Docker files to deploy the container and then run the code that we want. And then just kind of like move on from there to like save us more time. Because that was a real pain in the ass, is constantly like connecting to other people's computer and being like, you have to install this. So. Okay, so do you have any questions? Any opinions? Any thoughts? Should we be doing this? Yes. Okay. I really have nothing else except that this Docker file needs to get tested, or we need to do more reading and see what we might do. But I did have an error I'm stuck on. Can I run the pre-processing code? Um, so basically this code is calling this pre-dot single process is calling the BraTS toolkit that I talked about. And what it does is actually it pulls a Docker container and then uses the Docker container to run the code inside. But for some reason it's not working right now. There's an error associated with it because Windows and pathing, probably. So either I'll try to fix this bug tomorrow, or I'll work on the Docker file because this is untested. Or Deep Lab, I should say. I wanted to get Deep Lab to work, but I was too, yeah. So that's it. Yeah. All right. So yeah, I got nothing else, man. We're done. You want to mention anything or? Okay.